I apologize profusely, make the assumption that, like, everyone's had a chemistry class in the last 1 to 3 years. And of course, that's not always true. For instance, I myself have not had a chemistry class in quite a while. So there are certain things that we forget. And so it's probably a good idea that we get to go over some of this stuff again. And so once we finish chapter 6, I think it'll be time for our second lecture exam. So it might be, I'm leaning towards looking at next Thursday or the Tuesday after that, probably the Tuesday after that. I'll have to see how far we get with chapter 5 and chapter 6. I'd like to get all the way through chapter 6. So any other questions or concerns? Everyone's going to be quiet again today. You guys are killing me.
Sorry, just to confirm, so the next test might either be the 19th or the 24th?
Right.
Got it. Thanks.
Yeah. But then doesn't leave us a whole hell of a lot of time before the final. So, yeah, man, we're getting to the end awfully quickly here, now that I think about it. Okay, so basically what we've done so far, we've looked at hybrid orbitals, spend a lot of time on hybrid orbitals. And this week, I haven't posted the recitation yet. We'll spend a little more time on them. And today we're going to introduce a new concept of molecular orbitals, which is kind of a whole different animal, but is essential for explaining some things that hybrid orbitals don't explain particularly well. We've seen they explain a lot of things pretty well. The shape of methane, the shape of a lot of molecules is explained really well looking at hybrid orbitals, but they do fall down a little bit in some things, and that's what I'm going to introduce today. So when we left off, we were talking about, here we go. We're starting to talk about sigma bonds and pi bonds and the differences in them. And I want you to really sort of, drill this into your heads. Whereas sigma bonds are always, always, always made with hybrid orbitals. And you can see that here. Here's the hybrid orbitals of the two carbon atoms in ethylene, or ethene. And the whole purpose, the whole purpose for making hybridized orbitals was to maximize overlap. You have an orbital with one electron in it, you have an orbital with another electron in it. Well, if you want to make a bond between those two orbitals, you overlap them. And the stronger the overlap, the more overlap there is, the stronger the bond. And so by making these hybridized orbitals, you maximize the overlap, and so you get maximally stable bonds. And the key thing is that overlap is directly in between the two atoms. So here's carbon 1 over here, and there's carbon 2, and you can see that the overlap is directly in between. It's directly between them. So remember, a bond is nothing more than electron density in a particular place. And so if that electron density is directly in between those two atoms, that is a sigma bond. And it's strong because it's all that electron density is in one place. But then the question remains, well, where do double and triple bonds come from? Well, the double and triple bonds come from these hybridized orbitals, unhybridized orbitals, because the unhybridized orbitals are the ones that are left over, and those are p. Those are p orbitals. And you remember what the shape of p orbitals was, up and down, in and out, side to side. And so the ones that went side to side in between the two atoms got hybridized. And so along with an S. And so that's where the single sigma bond goes. The ones that weren't hybridized are going up and down, in and out. And so these unhybridized p orbitals meet both on top of the single bond and below the sigma bond. And so you have this sort of weird looking density of electrons that looks like a big, hot dog bun, both above the bond and below the bond. And that is a pi bond. And the weird thing to think about is that it's actually 2 electrons in there, the density of 2 electrons in there, both above and below. So you can see that it's spread out over a much greater region. And because the overlap isn't nearly as much as it is for a sigma, that bond isn't nearly as strong as a single bond. So when you have 1 pi and 1 sigma, you have electron density above and below the single bond. When we introduce a second pi bond, or a double bond, a triple bond now we have 2 unhybridized p orbitals, both up and down and in and out. And so we have electron density, let me go back. We have electron density above the bond and below, as well as in back of the bond, single bond, and in front of the single bond. So now you basically have electron density all the way around the atom. 2 electrons have a density directly in between, that's the sigma, and then you have 2 more electrons on top and on bottom, and 2 more electrons in back and in front. And so remember, always pi bonds are made with p orbitals. That's how I always remember it. I pop those p's. And the sigma bond, the single bond, is always made with hybridized orbitals, because the whole point of hybridized orbitals is to maximize overlap. Okay? So I think the folks who did the lab should have some drawings that kind of look like this. And for the folks who said, I can't draw worth a damn. Yeah, I can't draw worth a damn either. But I want you to give it a try. If you feel like, you just want to, copy and paste a picture, that's fine, but include a picture of your own as well. They should look something like that. So, remember we talked about bond order a little while, and bond order is going to become really important when we discuss molecular orbitals. Bond order is basically how much electron density is there between 2 atoms. That's really all it is. A single bond has a certain amount of electron density. Double bond has a little bit more electron density. The triple bond is even more. So here, this sort of gives you an idea of both what the distance is between those 2 carbon atoms and how much electron density there is. So here, this is, I keep doing that. Here we have our carbon-carbon single bond. We have like this much electron density around one carbon, this much electron density around the other carbon, and then this is in here, in the middle, that's how much electron density there is in between. That is your bond, okay? So these are non-bonding electrons that each carbon has. I mean, each carbon has non-bonding electrons, of course. And then there's bonding electrons that it shares with other atoms. So these 2 spikes are non-bonding electrons. And then the area in between is bonding electrons. So you can see as we introduce another bond, this goes up. Now we have a higher density of electrons between those 2 carbons. Then when we go to a triple bond, we get even more density in between those 2 carbons. But notice that it isn't linear. A triple bond does not have 3 times the electron density in between those 2 carbon atoms, because it isn't 3 times as strong. The strength of a bond is indicative in its density, in the electron density between those two atoms. So as you get a double and a triple, it doesn't go up in a linear fashion. It goes up a little bit and then a little bit more, because that pi bond is weaker than a sigma bond. So this is bond order of 1, that's bond order of 2, that's bond order of 3. But you remember there were certain, when we were drawing different Lewis structures, we saw that sometimes there was resonance in between. There may have been, you could move electrons around, what we were called delocalized electrons. And so we can have bond orders of 1.5, 1 1/3, 1 2/3, depending on whether those electrons are delocalized in an area or whether they're kept between two particular atoms. So this is the way of looking at double, single, double, and triple bond. Gives you the order, but it is not a linear response. A triple bond is not 3 times the strength of a single. A double bond is not twice as strong as a single. The other thing I want you to take away, go ahead.
What is a bond order again?
Oh, bond order just represents how many bonding electrons are between two atoms. If it's 1 pair, then it's 1. If it's 2 pair, then it's 2. If it's 3 pair, then it's 3. That's what we call bond order. And then sometime, and we'll get into this today, but when you remember a while ago, when you draw a Lewis structure, there may be more than one way to draw it. You can put the double bond here, or you can put the double bond there. They're both equally likely. So what you actually see is sort of, instead of one atom having a bond order of 1 and the other one having a bond order of 2, they're sort of averaged together, and each of them has a bond order of 1.5. And that is something that we'll return to, because that's really, really critical for molecular orbital theory. So basically it just boils down to how many electrons pairs are being shared. That's really what a bond order is. Okay?
Okay, thank you.
No problem. Thanks for asking. So let's look at the kind of bonds and orbitals in acetones. This is something we've sort of looked at a little bit, but it makes the point that I want to show. The first thing you do is draw a Lewis structure, and then you determine, okay, where the atoms go, where are the bonds between them, how many bonds are between them, how many lone pairs of electrons we have. And then we can figure out, based on the number of bonds each one has, we can figure out, well, what's the hybridization? Are there sigma bonds? Are there pi bonds? How many? And so this is what, I should probably use a darker color. Here we go. So we have 2 methyl groups. CH3 is called a methyl group. And those are just a carbon bound to 3 hydrogens, which is then bound to something else. So each one of these carbons, carbon 1 and carbon 2, are going to have 4 single bonds. So I think we can pretty much know what hybridization they're going to be. And then there's an oxygen bound to the central carbon with a double bond. So what sort of hybridizations do we have here? What sort of hybridizations would there be on carbon 1 and carbon 2? Because they have 4 bonding regions. What hybridization would they be? Everyone's forgotten already.
SP3?
That's right. That's right, SP3, because you need 4 bonding regions of equal energy. So I take my S and my 3p orbitals, I hybridize all of them together so that they're all equal. And so I have sp3 there, and I have sp3 there. What about the central carbon? What would be the hybridization of this carbon?
sp2,
Why is that?
because the pi bond or the double bond counts as one hybridized bond.
Right, so you have 3 regions of electron density there. So
Yeah.
in this instance, and another way to look at it, that's, you're absolutely right, is sp2. Another way to look at it is, how many sigma bonds am I going to form? How many sigma bonds? Because remember, all my sigma bonds have to be equal to each other. They're all single bonds. And so in this instance, I've got 3 regions of electron density, 3 sigma bonds and 1 pi. So it has to be sp2. So I got sp2 on my carbon, and I'm going to have a sigma bond and a pi bond there. Now, what about the oxygen? What's going to be the hybridization on the oxygen?
Also sp2.
Right, right. So but instead of having 3 sigma bonds, it's only making 1, but it does have these 2 lone pairs. And so it has to arrange those 2 lone pairs and the sigma bond in a way that they maximize the distance between them, which is the trigonal planar. So that is sp2 as well. So let's have a look, see what that looks like. Oh man, you got them all. Excellent. Yeah, so the question then becomes, what kind of orbitals are making all those bonds? So we've got 2 sp3s on the outside. We have an sp2 on the carbon, and we have an sp2 on the oxygen. So we want to, if we were to draw a diagram of what orbitals make all those bonds, it would look a little something like this. So notice that all of the sigma bonds are hybridized. So we have sp2 and sp2 for the sigma bond of the carbon oxygen double bond. That is a sigma bond. The first one is always a sigma bond, and that is always a hybridized orbital. The lone pairs are also in hybridized orbitals. And so for the other carbons, the ones on the outside in the methyl groups, they're all sp3 hybridized. And they all bind with 1 hydrogen, 2 hydrogens, 3 hydrogens. And then here is where you see the hybridization on one and the hybridization on the other overlapping. So I have carbon in the methyl group with an sp3 hybridization overlaps with this carbon's sp2 hybridization. And since they're both hybrid orbitals, that is also a sigma bond. And so what you have left over, that accounts for all of the sigma bonds and all of the hybrid orbitals as well. There's no more hybrid orbitals left. However, since carbon and oxygen are both sp2 hybridized, that means there is a p orbital left over. And it's that p orbital that forms the pi bond. So there's the pi bond with electron density on one side and electron density on the other side. The way this is drawn is a little misleading because it has 2 electrons on one side and none on the other. It's actually equal density on both sides. So one question I have about this is, how come we don't hybridize the orbital in hydrogen? Why doesn't hydrogen have hybridized orbital as well? Because it's forming a sigma bond.
Only has 1 electron density region.
Mm-hmm. And what else? That is correct.
Oh, it's because it only has an S shell.
That's right. There's only an S shell. What's it going to hybridize with? That's it. That's the only place it has to put an electron, is the 1s orbital. That's it. So it doesn't have any p orbitals to hybridize with, because there aren't any in the first shell. So it can't. It's one of those elements that can't form hybridized orbitals. In fact, it's pretty much the only one other than helium, but helium doesn't form any bonds, so it's not making any hybridized orbitals. So hydrogen does not have that ability. So it is always going to be 1s1. That's it. It can't do anything else but make that particular orbital. One other thing I want to point out here that I should have probably pointed out when I showed you the ethene. Actually, I'm going to come to it in a second, about how you can rotate single bonds and you can't rotate double bonds. Yes, I put that slide here for a reason. So if we were making these models, you will see that when you make a single bond, you have your two little balls, you put a stick in between them, and you can spin them around because there's nothing stopping you from spinning. Anything with like a single axis, you can spin it around. But when you make a double bond, you now have two axes between the two atoms. And now they're sort of stuck together. And that really does also show itself in the chemistry of these molecules as well. Because notice, when I have a double bond, I now have pi density above and below my single bond. And because I have electron density both above and below, the minute I try and bend that, I now get pushback. I get electron repulsion because I have electron density here, I have electron density there. So if that molecule moves anything out of the plane, it now has electron repulsion. So the lowest energy it can maintain is that planar shape. If it moves, it gets repulsed and pushed back into place. And so I could no longer rotate around a double or a triple bond. This is locked into place. And that's why we have something called cis and trans. Cis means you have a group on one side of the double bond. In this instance, I've got chlorines. So I've got a chlorine here. We got a chlorine here. And notice they're on the same side of the double bond. And they can't move. They're stuck there. So I have something with high electron density next to something else with a high electron density. That makes this one polar, because I have more electron density on the bottom. I've got more electrons here and here than I do on the top. I got hydrogen on the top and I have chlorine on the bottom. So there's less electron density on the top, there's more electron density on the bottom. And then when you have a difference of electron density from one side of the molecule to the other, that's polar. This is exactly the same molecule on the bottom. They're both C2H2Cl2. It's exactly the same formula. However, this one has a chlorine on the top, and that one has a chlorine on the bottom, and they are locked there. They cannot move. Notice what happens to my dipoles. So now, one of the bond dipoles is pointing up and away. The other dipole is pointing down and away, and they cancel out. This one is nonpolar. So I have the exact same molecule with slightly different shapes. One of them is polar, one of them isn't. And you can actually separate these based on their boiling point. The polar molecule boils at a slightly higher temperature than the nonpolar molecule, even though they're pretty much identical in every way. So does anyone have any questions about cis and trans? When you get into organic chemistry, you'll be dealing with this a lot. And of course, you're all going to take organic, I know, because it's fun, fun, fun. So any questions about cis and trans? Because we're going to get into the good stuff now. Why I've been lying to you this whole time about hybrid orbitals. A liar. Okay. All right, here we go. So we got some problems with the hybridization model. There's a couple of problems. Hybridization isn't always consistent with observed molecular shapes. I've been lying to you this whole time, and I just feel terrible about it. But 99% of the time, the actual shapes that we see of these various molecules agree very, very well with the hybrid orbital model, but not always. For instance, here we've got just regular old hydrogen disulfide, that stinky gas, natural gas. This is the molecule that gives that rotten egg smell. And so when we look at the bond angles here, we would predict that sort of like, just like water has that bond angle. We would expect it to be slightly less than 109 because we have these two lone pairs on the oxygens that like push these together. So we'd expect it to be a little less than 109. And in water it is, it's around 104 or something, 103. So well, that makes sense. But look at H2S. That bond angle is 92 degrees. That's a lot less than 109. In fact, that kind of looks like the sort of bond angle you would get if these were just p orbitals. Because remember, what's the angle difference? What's the angle between p orbitals? Anyone remember? We have up and down, side to side, in and out. What are the bond angles? What are the angles between all those three orbitals?
90.
Yeah, they're 90. And you look at the hydrogen sulfide, that's pretty close to 90. Might it just be unhybridized orbitals for that one? Well, if it's unhybridized orbitals for that one, maybe it's unhybridized for other ones as well. And when we look at the d orbitals, we like make computer programs of what are the energies of s orbitals, what are the energies of p orbitals, what are the energies of d orbitals. We run all these calculations. We see the d orbitals really don't hybridize very effectively with s and p because they're much higher energy than s and p. They don't mix particularly well. And so coming up with a way to sort of mix those together and hybridize them is really hard to do. And so a new theory came to be around the 1970s or so. And it goes back again to waves versus particles, just like all of quantum mechanics is dealing with are electrons waves or electrons particles. Well, they're both. If we treat them as waves, remember, like Schrodinger did, he came up with the S and the P and the D and the F. And, okay, good for you. That was for atoms. And Schrodinger dealt with atoms only. And that perfectly explained the periodic table. And so someone else came along, like 70 or 50 years later, I guess, and said, well, if atoms can have wave functions to describe where electrons are, how come molecules can't do that? Everyone sort of sat back and went, yeah, how come molecules can't do that? And so basically what the theory is that you take atomic wave functions, basically orbitals, right? and you combine them to form molecular orbitals. Orbitals, wave functions, same thing. They basically just tell you where electrons are in space. So if I add two atomic orbitals together, I get a molecular orbital. But remember, waves also subtract. So I can remember when two waves are coming together, either they're both peaking at the same point, and so I add them together, I get an even bigger wave, or one of them is peaking and the other one is troughing, and I add them together, I get Bupkis. And it's the same thing here. So when I add two atomic wave functions, I get a bonding molecular orbital. And that has a region of high electron density in between the two atoms. That's what a bond is. High electron density between the two atoms. I've been sort of saying that for a while now. On the other hand, you also have to subtract those orbitals as well, because waves add and waves also subtract. If I subtract those two, I get something weird called an anti-bonding molecular orbital, which has, if you remember what a node is, that is a region of 0 electron density between the two nuclei. So if there's 0 electron density between the two nuclei, that means no bond, nothing. So let's see what those actually look like, because these make some pretty weird. If you thought S&P and everything else was weird, these things are really kind of crazy looking. So again, just to go back and show you the difference between addition and subtraction. So remember, when we looked at our waves, we looked at the amplitudes. We added them together. So here, I've got an atom 1, and I've got atom 2. And here's my density of electrons around atom 1. Here's my density of electrons around atom 2. And there's some overlapping. And where there's overlapping, I get a bond. I get a region of electron density in between atom 1 and 2, and that is a bond. Okay, but also they can completely cancel out. Here I got my region of electron density. Here I've got my region of electron density. I add those two together and I get nothing. There's no electron density between these two atoms, and that is anti-bonding. So it just matters whether am I adding or subtracting. When I add, I get bonding. When I subtract, I don't. So here's an example. This is the man who actually came up with the theory. He's a fascinating individual. He was born in Austria, and the British got him out of Austria just before World War II started, because they saw what the Germans were doing. He was Jewish, and they saw what the Germans were doing. They got a whole bunch of kids out of both Austria and Germany before World War II started. So he moved to England, and eventually made his way to Canada, where he got his undergraduate degree, and then went to the United States to get his PhD, and stayed in the U.S. and was a professor at UC Santa Barbara for, I think, around 30 years or something, and then won the Nobel Prize in 1998. Like a really, really cool guy. There's a bit on him. This is actually from your textbooks, if you want to read a little more about Walter Cohn. It's fascinating life. And so here's the comparison, basic comparison, the breakdown between the two theories. So the one we've been learning about so far, valence bond theory, which is the hybridization model. That's bonds localized between a pair of atoms. I got a bond here, I got an atom here, I got an atom here, there's my bond. But when we look at molecular orbital theory, it considers electrons to be sort of delocalized around the whole thing. And we're just going to add together how many electrons are considered bonding electrons, how many are considered anti-bonding electrons. So that's one major difference. Valence bond theory creates bonds with overlap of atomic orbitals, p for pi bonds, and hybrid orbitals for sigma bonds. Molecular orbital theory makes molecular orbitals, either sigma for bonding, sigma star for anti-bonding, pi for bonding, or pi star for anti-bonding. And I'll show you what those look like. So again, sigma bonds, pi bonds, yes. And then with molecular orbital theory, yeah, they're both sigma bonds and pi bonds, but they're really depending on where the electrons are. Are they in bonding orbitals or anti-bonding orbitals? I'll show you what those are. The nice thing about valence bond theory is it predicts molecular shapes based on regions of density. We can understand that. I got electrons here, and I got electrons there, and I got electrons here. Okay, that's going to be a planar shape. That makes sense. What molecular orbital theory does, it predicts the arrangements of electrons throughout the molecule, like the whole thing. It could be like a really big molecule, and it's basically going to predict how many are bonding, how many aren't, and what are the physical properties. Valence bond theory needs multiple structures to describe resonance, as I mentioned before. If you have a double bond on one side of an atom and a single bond on the other, sometimes you can move that double and single bond around. Basically, what you get is an average of a double on one side and a single on the other. Molecular orbital theory doesn't do that. It directly tells you what the bond order is going to be between two atoms just by counting up the electrons. It does not need multiple structures to describe that. It just gives you that structure. It also makes some other predictions that are kind of interesting as well. And I'll show you what that is. So this is what these things are going to look like, okay? So here we got our poor little hydrogen atoms. And again, hydrogen cannot form hybrid, they can't hybridize. They only have the 1s1. There's no other place to put another electron. So I got my two isolated atoms in space. And the closer they get together, the more and more that electron density gets moved between the two of them, and then a bond forms. If I add those two 1s orbitals, I get something that looks like this. There's a little bit of electron density around each atom, and there's electron density in between. That's my bond. When I subtract those two orbitals, and that's the weird thing to think about, when I add them together, yeah, that makes sense that it kind of looks like that. But if I subtract them, they basically go back to looking like they did before, but basically pushing the electron density away from each other. So that electron density moves away from the other atom. So I've got this mode, this density around atom 1, this density around atom 2, and notice there's nothing in between. There's no electron density in between the two hydrogen atoms. Therefore, no bonding. Okay, and we call that the anti-bonding. So we have sigma 1s, sigma bond, single bond, 1s, because that's where the electron is. And if that is a bonding molecular orbital. If I have two electrons in my bonding orbital, I get bonding. If I put electrons in the anti-bonding orbital, and that's sigma, that's what the star means. Always look for the star. The star means not bonding. So if the star is there, that means if I put electrons in there, they will not be bonding with each other. And it's the number of electrons that are in bonding orbitals versus the number of electrons in non-bonding orbitals that determines whether a bond's going to form and what the bond order is. So let's look and see with just this particular model. So we're looking at what a molecular orbital diagram looks like. You sort of remember what the regular atomic orbital diagram look like, S and P, and we filled in made the little boxes for the different orbitals. We put electrons in. This is the same thing. It's all the same rules. It's just organized slightly differently. So just like an atomic orbital diagram, we put them relative energies. The lowest energy orbitals go on the bottom. And then as we increase in energy, we add new orbitals. We start at the lowest one and we start adding electrons, and we go to the next one, and then the next one, and then the next one. So the molecular orbital diagram shows the atomic orbitals. So if I have atom 1, atom 2, it shows the atomic orbitals of atom 1 and atom 2, all the S and the P and everything. And then it shows you how those things are added together. And then we figure out what the bond order is going to be. We take all the electrons that are in bonding orbitals, we add all those together. We take all the electrons in non-bonding orbitals, we add them together, and divide by 2. Because a bond is how many electrons? How many electrons in a bond?
2.
2, exactly. So if I have if I have 2 electrons and a bonding electron and no other electrons, that's a single bond. And let's see what that looks like. Here's the simplest bond we're going to deal with. So this is what the molecular orbital diagram looks like. So we got a couple things going on here. Here's the real simple atomic orbital for this hydrogen, hydrogen 1, and there's hydrogen 2, and there's the atomic orbital for hydrogen 2. So when I mix those two, so that is just, you always see that with the molecular orbital. You start with the atomic ones, and what 2 atoms are going to be making this bond. Put atom 1 on the left, atom 2 on the right. You include the atomic orbitals for the electrons that are going to be bonding. That is really a key, and I'll show you an example of this later. If we don't include electrons that will not be bonding, for instance, chlorine. Remember, chlorine has 7 valence electrons, but are all of them involved in bonding? Usually not, right? Usually we just have 2p, actually 3p for chlorine. 1, 2, 3, 4, 5. And it's usually that one electron that's involved in bonding. None of the other ones are. They're valence electrons, sure, but they don't actually participate in bonding typically. So it's just that one. So we would say that that 3p electron is the one doing the bonding. We wouldn't really include the other ones. But here we have our 2 hydrogens, 1 and 2. And when we add them, remember, we'd have to do 2 things. You have to add them, and we also have to subtract them. So when we add them, this is our molecular orbital. This is our lowest energy molecular orbital. We start with this bonding. That is a lower energy because you're forming a bond. That is going to be more stable than not forming a bond. So my sigma is going to be lower. When I subtract them, my sigma star is going to be higher. So this is my bonding. This is my anti-bonding. Well, I've only got 2 electrons. I got this one and I got this one. And you're adding them all together. You're adding all of them. So I've only got 2. So I go 1, 2, that's it. And so I've got 2 electrons in a bonding orbital, and I got none in an anti-bonding orbital. I figure out what the bond order is. 2 in bonding, none in anti-bonding. That's 2 times 1/2 equals 1. My bond order is one. Single bond. There you go. That's a single bond between hydrogen and hydrogen. Any questions about this? I'm trying to go through this kind of slowly because it is kind of new and scary. But basically, I'm just adding orbitals, atomic orbitals together. I'm adding them and I'm subtracting them. That's all I'm doing. And then we're seeing what kind of bonds come out of this. So anyone have any question about how hydrogen works? I have 2 bonding electrons and I have 0 anti-bonding electrons. That gives me a bond order of 1. So do you see how we add them and subtract them?
Professor, where does the half come from?
There's 2 electrons in a bond. So if I have 4 electrons in bonding orbitals and no electrons in anti-bonding orbitals, I'm going to make 2 bonds, right? Because each bond is 2 electrons. That's still true. We didn't change the rules about that, because even when we were looking at hybrid orbitals, we had 1 electron in one hybrid orbital, 1 electron in the other hybrid orbital. And when they got together, they made a bond, but there was 2 electrons in it. Same thing is true here.
Okay.
So that's why we divide by 2, because basically it tells us if we have 4 bonding electrons, if we have a net 4 bonding electrons, we have 2 bonds. If we have 6 bonding electrons net, we have a triple bond. Okay.
Okay.
Gets a little more confusing after this, so I really wanted to make sure we were nailed in on this one. So what are the rules for filling these in? Just like atomic orbitals, we go in order of increasing energy. And like I said, the bonding orbitals are going to be lower energy because when you form a bond, you have a more stable structure. So you're always going to have sigma is going to be lower energy than sigma star. Pi, that's not pi. Pi is going to be lower energy than pi star, because whenever you make a bond, you lower the energy. It's the whole point of making bonds, is to lower the energy of the molecule. So we arrange the molecular orbitals in order of increasing energy, just like we did with atomic orbitals. Remember, S were the lowest, followed by P, followed by D, followed by F. And that is still true here. Now, a molecular orbital can hold a maximum of 2 electrons with opposite spins. Well, that sounds familiar. Just like our atomic orbital. If we have an orbital, we have our little orbital house with room for 2 electrons. First one goes in spinning up, second goes in spinning down. Same thing here. So when we looked at the molecular orbital for hydrogen, we got sigma 1s with 1 spinning up, 1 spinning down. Orbitals of equal energy, and that'll happen when we get pi, because p orbitals, when we have more than a single orbital, we have a pair of them or so, they're with equal energy, we half fill them with parallel spins. So for instance, if I have pi, 2 pi bonding orbitals, I go 1, 2, and then I come back 3, 4, just like you did for p orbitals in the atomic case. Remember, when we had 3 p orbitals, we went 1, 2, 3, and then we went back 4, 5, 6, because they were all equal energy. So they would spread out before we started putting them together. Same is true here. So, and then we just show you the number each contains, the number of electrons in each orbital, and we add them together. How many are bonding? How many aren't? How many are anti-bonding? They're not just aren't bonding, they're actually anti-bonding, causing bonding not to take place. So what does that look like when bonding actually doesn't take place? Give you some examples here. So here we have, now instead of hydrogen, we have helium. So now we have dose electrons to deal with. So what if we had helium with a charge or diatomic helium? So helium with a charge, that would be one helium atom has 2 electrons, like a normal helium atom would, and the other helium atom was lost an electron, so it was positive. It was a positively charged cation. Not very likely that that's going to happen. The thing is, theoretically, would that make a bond or not? Well, let's see. According to molecular orbital theory, yeah, it might. So we've got 2 electrons in helium, and we have only 1 electron in helium plus. So I got a total of 3. So the first 2 go into low energy orbital, my sigma 1s, because helium's only got the 1s. But I got another electron left over. That goes in the star, the anti-bonding orbital. Then I'm done. Then when I figure out what the bond order is, I've got 2 bonding, 1 not bonding. 2 minus 1 is 1, times 1/2 is 1/2. So it sort of predicts that there would be a bond formed, but it would be weak. You would have a weak bond is possible between helium and a helium ion. Okay, whatever. What if I have 2 helium atoms? Now we know that 2 helium atoms do not make a bond. What does the atomic orbital look like for that? It would look like this. So we've got our 2 atoms. Helium 1 has its 2 electrons. Helium 2 has its 2 electrons. So they both have 2. Excuse me. So now I have a total of 4 electrons. I have my sigma 1s, this is my bonding. I put my first 2 electrons in there. Those are my bonding electrons. I got 2 electrons left over. They go in the higher energy star orbital, and I put 2 electrons in there. Done. What's the bond order? Well, I've got 2 bonding. I've got 2 anti-bonding. 2 minus 2 is 0. My bond order is 0. That means this bond does not form, because I have the same number of electrons that are bonding, the same ones that are anti-bonding. You add them together, you don't get anything. So basically, you're taking 2 and minus 2, adding them together and getting 0. So do you see how this works? It predicts that helium will not bond, and that's true, obviously. Do you see how that works? Why one bonds and one doesn't?
How do we know what goes in the anti-bonds again?
You're just counting all the electrons. So here, I've got 2 electrons here. Basically what you do is you start with one side and the other side. How many electrons do I have on one side? My atomic orbitals say I have 2 bonding electrons over there. I have 2 bonding electrons on the other side. And then I'm just going to mix them together. So I've got a total of 4. So when I mix these 2, remember, I'm taking 2 atomic orbitals and I'm adding them and subtracting them. That's what we always do with these molecular orbitals. I add them together and I subtract them. The addition of them first gives me bonding. That's lower energy. So I put my first 2 electrons there. I have a total of 4 I've got to fill in. So the first 2 go there. The second 2 go to the higher energy orbital. And I put 2 there. Then I'm done. There's no more orbitals and there's no more electrons left. So now I have 2 in the bonding, 2 in the anti-bonding. They basically cancel each other out, and so I don't get any bonding. Yeah, you just take the atomic orbitals for one atom, the atomic orbitals for the other atom, and then you add and subtract them.
So we would fill the bonding one first fully,
Yes.
and then the antibond. Okay.
Right,
thank you.
exactly. That's why if you take one of these electrons away, now you only have one electron that goes in the antibonding orbital. And that makes this bond theoretically possible because I have more electrons in my bonding than I do in my antibonding. And because I have more electrons bonding than are antibonding, well, some bonding's got to take place. So that's at least theoretically possible. 2 helium atoms will not bond under any circumstances because you have the same number of electrons that will be bonding and then physically keeping that bond from forming. And so when you add them together, you get nothing. Nothing happens. And that's what we see. Nothing happens. Right. Let's look at a couple of others. So we're going to look at hydrogen, but if hydrogen had either one fewer electron or one more electron, and then we would figure out, are these possible? Can we actually like form these? And we then write where its electrons are going to be. So remember, hydrogen only has 1s electrons. The only difference is, does one atom have more than one or less than one? If we have H2 plus, then one of the hydrogens has an electron, the other one doesn't. It's just a proton. If it's H2 minus, one of the hydrogens has 1 electron, the other one has 2. It has an extra electron. So we'll put those on either side, add or subtract the orbitals, and then see what we get. So just like I said, H2 plus has only 1 electron, H2 minus has 3. So let's see if we make those. So if this is H2 plus, I would have hydrogen on this side and H plus on the other. So how many electrons do I put in the atomic orbital here? Remember, there's a, yeah, I'm having a hard time. Remember, there are atomic orbitals on the outside and molecular orbitals in the middle. So here I'm dealing with just the hydrogen first. So how many electrons would a hydrogen atom have?
Just one.
Just one. Exactly. There it is. Now I'm done for that one. H plus is how many electrons? How many electrons does H plus have?
0.
Yeah, doesn't have any, exactly, none. So I don't put anything there. So now, basically, I just have 1 electron to put in my 2 orbitals. Remember, I have sigma when they're bonding, sigma star when they're not. And I just got 1, and it goes, where does it go? So I just have the 1 electron, where does it go?
Anti-bonding.
So I would put it there first? Why would I put it there first? Remember, the rule is always, even for atomic orbitals too, any orbitals, you always start by putting your electrons in the lowest energy orbitals available. What's my lowest molecular orbital available? My lowest energy molecular orbital. Which one is it? Is it the bonding or the anti-bonding?
It's a bonding orbital. But my
Right.
question is, how come they can bond in when the other atom has no electron?
Well, this would be a bond between a hydrogen atom and a proton. And and the idea is, can this form a bond or not? I don't know. Let's find out. Basically, can one electron be shared between two protons? Because remember, a hydrogen atom is just nothing but a proton with a single electron. So this is asking, can I have two protons with one electron sort of circling them both? Is that theoretically possible? So where do I put that only electron? Do I put it in the anti-bonding orbital or the bonding orbital?
The bonding orbital.
Yeah, it's the lower energy one, right? Always put electrons in the lowest energy orbital first. Always, always, always. That's where it goes. It goes here. And I don't have any electrons left. I'm done. So my electron configuration is sigma 1s 1. That's it. I've got one electron in a sigma bonding orbital. That is it. So what's my bond order going to be? Remember, I take all my electrons that are bonding, subtract all my electrons that are anti-bonding, and divide by 2. So what's my bond order here?
When the bond order is lower, does it mean it's stronger?
No, it means it's less strong. Yeah, the higher the bond order, the stronger the bond. So 1 is a single bond, 2 is a double, 3 is a triple. But as you've seen, we can have bond orders of like fractional bond orders. So we're not sharing 2 electrons. If we're sharing like 3 electrons, that would be a bond order of 1.5. So in this instance, we're only sharing 1 electron.
Wait, so if the sigma bond is stronger than the pi bond, then how come it has a lower bond order?
Well, I'm just asking, what is the bond order here? With this particular example. Yes, Rye, you're right. So what's the bond order here? I have 1 electron that's bonding, and I have buckus that's non-bonding. What's my bond order? If you want to read the chat, Rye has it correct. I want someone to say it out loud.
One half or a half?
Yeah, it's 1/2. I know that sounds weird, right? 1/2. The hell does that mean? It means 1 electron is being shared. That's what that means. And by definition, that's exactly what's happening here. Remember, I have a proton here. That's 1 hydrogen atom. I have a proton there. That's the other hydrogen atom. And they're sharing 1 electron. That's a bond order of 1/2. Because you need to share 2 electrons to form a proper bond. So this would be a weak bond. Theoretically, it's possible, but it's a weak bond because it has a bond order of 0.5 or 1/2. So it can form, it's weak, but theoretically it can form with a bond order of 1/2. Now, what if I have hydrogen here and hydride ion over here? Remember, hydride is hydrogen with 2 electrons. It is a negative charge, hydride ion. And so, how many electrons are in my atomic orbital for hydrogen?
1.
1. There we go. How many electrons are in my hydride ion or atomic orbital?
2.
2. 1, 2. So now I have a total of 3 electrons. And I then start, I got 3 electrons available for bonding, and I start putting them in my molecular orbitals. So where do I start filling in?
2 at the molecular orbital.
Which one? I got 2 of them here.
Oh, at the bottom.
Right. Which, so what do I call this? Remember, what do I call this?
The bonding orbital.
What's this symbol?
Sigma.
Sigma, right. So I put it in sigma 1s. 1, 2. Remember, the first one always spins up, second one always spins down. I have 1 electron left. Where does it go?
The anti-bonding. Sigma.
Right. Goes in sigma star, pointing up. What is my bond order? You see, I have a different arrangement of electrons this time. What's my bond order now?
So 2 minus 1 equals 1, then times half will give you 1/2.
Yeah, it's 1/2 again, exactly. Because I have 2 bonding minus 1 here that's anti-bonding. And then I divide that by 2. And that is 1/2. And the reason that's 1/2, just, oh, go ahead.
By 2. Is that always 2?
Always 2. Because a full bond, a real bond that we're sort of, typically think about is 2 electrons being shared, right? 1 electron from one atom, 1 electron from the other atom. They share them, that makes a bond. So that's 2 electrons make a bond. In this instance, though, I have my hydrogen here with its electron. I have my hydrogen here with its electron, and there's another electron. There's 3, right? So basically, these 2 are sharing 1 more electron. So there's some electron density in between them that's equal to a single electron. That electron density in between them of a single electron is half a bond. And so it has the same bond order as if there was only 1 electron shared between the 2 of them. It's the same electron density. When I had just 2 protons, let me erase that. The previous example, I just had 2 protons, proton here, proton there, and a single electron in between them. That's the same bond order, 1/2, because it's just 1 electron being shared between 2 atoms. So it's the same thing. So let's see if we got that right. Yeah, so we would predict that each one of those is theoretically possible. Each one of them has a bond order of 1/2. And this is how you write the electron configuration for molecular orbitals. You say which molecular orbital it's in, and then how many electrons on top. So sigma 1s, put it in brackets, 2 in bonding, sigma star 1s, brackets 1, anti-bonding. Okay, let's go to something a little more difficult, because we all get this now, right? Let's start adding, going up a little bit more. So here I've got lithium. Now remember, lithium only has that single electron in a bonding orbital. The 1s is not bonding. The 1s are not valence electrons. So lithium has 1s2, 2s1. These don't bond. This one does. So we would use exactly the same rules that we did with hydrogen. So when we look at we adding 2 electrons together. Now instead of sigma 1s, now we have sigma 2s, because that's where the bonding electrons are in sigma in 2s. So when I add my 1 bonding electron from this lithium and my 1 bonding electron from that lithium, I put 2 in the bonding, I have none left over. And so, yeah, this bond can form. I can make a diatomic lithium molecule. That works. But what about beryllium? Now we have another electron. So we've gone from lithium 3 electrons to beryllium that has 4. It has 4 total electrons, but only 2 of them are valence electrons, the 2s. It has 2 electrons in the 2s. Beryllium has lithium only has 1. Can I make a beryllium diatomic molecule? Well, I have 4 bonding electrons. 2, 4. Add them together. 0. So I have 2 bonding, 2 anti-bonding. So that is not going to form. Just like helium is not going to form. It has 2 valence electrons. 2 valence electrons plus 2 valence electrons, that doesn't work because you have 2 bonding, 2 anti-bonding. That doesn't work. So the same is true whether those bonding electrons are in 1s or 2s or 3s or 4s, doesn't matter which one. If you only have those 2 bonding electrons and they come together, that's not going to form. Okay?
Professor,
Yes.
in the lithium, why doesn't an electron go into the sigma star?
Because there's only 2. I only have 2 electrons. Oops. I only have 2 electrons there for bonding. Remember, we're only dealing with valence electrons, not core electrons.
Okay.
So if I have like uranium or something with like, a whole ton of electrons, I'm not dealing with any of the core electrons. These are just the outer shell electrons.
Okay.
So so still valence electrons are valence electrons. That has not changed. So if it's in group 1, it is 1. If it's in group 2, it is 2. Group 3, so on and so on and so on. Things get more interesting though when we go from 3 to 4 to 5 to 6, when we start moving down. So now let's start looking at some of the really weird shapes. So we looked at S. S was fairly straightforward. You add S orbitals together, you either get density in between or away from. Same is true with P. So remember, Px, that is the P orbital that is between the 2 atoms. So this is my atom 1 and my atom 2. My X extends out from one and the other. So I get some overlap here. So when I add them together, I get greater electron density in between. When I subtract them, I push that electron density away from the middle and toward the outside. Those are anti-bonding orbitals. Those are also sigmas. Why are these are p orbitals? Why is that a sigma bond? Why are these sigma orbitals? Can anyone tell me why that is? I thought p orbitals made pi bonds. How come these p orbitals are making sigma bonds? Am I lying to you again? I really need to stop doing that. Why is this a sigma bond rather than a pi bond? P orbitals make pi bonds, right? Don't they? How come this one doesn't? Don't be afraid of being wrong. I won't yell at you for more than 5 minutes. What's different about this p orbital and the other two?
Is it just one bond?
It's just one bond. But why is it a sigma bond and not a pi? I thought p orbitals made pi bonds. It was the whole point of popping my p's. It's that p orbitals made pi bonds. This one isn't, though. This one's making a sigma bond. What's up with that? What's the definition of a sigma bond?
Because it's end to end instead of side to side.
It's end to end. So where does that put the electron density?
Right between them.
Exactly. That is the difference. Excellent. That's the difference. Because when I have these two p orbitals directly overlap with each other, because they have, that's in the x direction, the x-axis. Remember, the x-axis is in this direction. Y-axis is in this direction, and the z-axis is moving in and out. So the x-axis is right between the two atoms. So they directly overlap. And when they directly overlap, they form. That means, by definition, that is a sigma bond. On the other hand, the py is above and below, just like we saw before when we were looking at what pi bonds look like. So these are different. These are going up and down. So if these are my two atoms, one here and one there. The electron density isn't in between them. It's above and below. So when I add them together, I get electron density above and electron density below. That is a pi bonding orbital. When I subtract them, basically what I'm doing when I subtract them is I'm moving the electron density of these two away from the two electrons. So when I move them away, I basically move them away like this. I'm moving them further apart. When I subtract them, they're moving them further apart. So they basically look like balloon animals that I've sort of stretched. I've sort of pulled them away from each other. That's what a pi anti-bonding orbital looks like. That electron density is as far away from the other atom as it can be. There's no way to overlap this and this. They do not, they're as far away from each other as you can get. They will not form a bond in any way. In fact, they will anti-bond. So the bonding orbital is what we're familiar with. It looks like the good old hot dog bun we've all come to know and love. The anti-bonding pi orbital is really far from each other. So let's see what that looks like when I start adding p orbitals this time. So I'm going to end here. What I want you to not think too much about is this mixing here. All this means is that when there's not much pull, like with atoms with not nearly as high proton density in the nucleus, they don't pull on the outer shell electrons as much. And the difference in energy between S and P get pretty small, and they sort of mix together. When you have more pull on outer shell electrons, like larger atoms, they don't mix. The difference in S and P is bigger. And so you get a different order of orbitals. But don't worry, if when I ask you a question on a test about this, I will give you the diagram. And it's just up to you to figure out where the electrons are going to go. Okay, so this is the mixing is a little beyond an introductory class. I just want you to know it's there, but not to worry too much about it. Because all it means is it changes these two right here. It changes the order of sigma and pi bonding. Without mixing, sigma gets filled first like we would expect. When they mix a little bit, actually the pi orbitals get filled first. But let's not worry too much about that right now. Let's just think about where we would put our electrons. So yeah, there's the difference. Sigma 2p moves from being the first bonding orbital outside of sigma 2s to being the second one. That's the only difference. So now we have 2s bonding and we have 2p bonding. 2s bonding, 2p bonding. And then we just add those electrons together. So one thing I want to point out before we go, this explains a very important thing that was unexplained for a really long time. For a really long time, it was known that liquid oxygen is magnetic. That when you pour liquid oxygen in between, this is a strong magnet. Notice that the liquid oxygen gets pulled towards one side. It's magnetic. You pour liquid nitrogen in between and it just falls right through without being attracted to one pole or the other pole. Oxygen doesn't. Oxygen gets pulled towards one pole. So where I'll pick up on Thursday is we'll draw the hybrid orbitals for oxygen, and we'll see that it predicts that oxygen should not be magnetic, but it clearly is. And that was one of the reasons why molecular orbital theory came along, because not only does the hybrid orbital theory break down sometimes when it comes to shape, it also breaks down sometimes when it comes to physical properties like magnetism. And so that started some people thinking, well, maybe there's more to this than meets the eye. Okay, so we'll leave it there. We'll come back to it on Thursday. Any questions before we go? I imagine everyone's just sort of scratching their heads right now.
So for the test, are we going to have to actually draw the hybrid orbitals?
I will give you this. So if I ask you to draw, if I asked you to tell me whether two atoms are going to bond and what's the order they're going to make and whether or not it's magnetic, I'll give you this.
No, I mean the sp2 orbitals.
Oh, what they look like?
Yeah, we're going to have to draw the ones from the valence bond theory.
Well, those are, no, not really. I mean, you're just going to have to know where they are. Like, know that it's an SP or an SP2 or an SP3, and then where it would be around the atom. Like an SP would be on one side or the other side. An SP2 would be SP2, SP2, SP2 in a plane, and then SP3 would be 4 around in a tetrahedral shape. So you have to remember that. But like physically what they look like, no, not really.
Okay, thank you.
Yeah. Yeah, just know where they are and what hybridization it is. But for these sorts of questions, what I would do is basically give you the two atoms. Let's say if I said, what would a sulfur oxygen bond look like? So I'd give you which electrons are bonding, give you this, and then you would have to fill in where the electrons go. Add the bonding electrons, anti-bonding electrons. Tell me what the bond order is, and then whether or not it's going to bond or not based on that, and then whether or not it's magnetic. And we'll get to figuring out how to calculate the magnetism on Thursday. So this afternoon, I'm going to post for my two groups. I'm posting the recitation. The first two questions are basically on this, and then the rest of them are on going back to hybrid orbitals to make sure we have a good understanding of that. I'll be posting that right now. So any other questions? Okay, everybody. I will see my two groups this afternoon. The rest, remember, I have office hours tomorrow if you want to ask me questions about this or anything else. Tomorrow at 11. And then if not, I will see you on Thursday.